Hey Wheaton North, Mr. Yergler here. We've talked in a previous notes video about the IMFs and the evaporation rate, but this one is a little bit different. This is about IMFs and the boiling point. It's similar to, but not completely identical to evaporation rate. So that's why we're kind of pulling it out as a completely separate video. So let's go ahead and take a look at boiling point. Boiling point is the temperature at which a liquid will boil. Or in other words, the temperature at which a liquid will evaporate from throughout the entire liquid. So if you think back to evaporation, evaporation happens only at the surface of the liquid, right? Only surface molecules are randomly getting enough energy to kind of escape into the air. When you boil something though, you're providing so much energy to it, you're heating it up so much, the molecules are moving so much that they can break free from each other anywhere in the liquid. Okay, so not just at the surface where they can escape, but also they can separate and form bubbles on the sides, down below, underneath, anywhere in the liquid they can do this. And that's because you're providing so much energy, or just enough energy to separate those molecules throughout the entire liquid, right? So water boils at 212 degrees Fahrenheit, but let's remember that it's 100 degrees Celsius. We're not going to really use Fahrenheit ever in science. So water freezes at 0 and boils at 100 degrees. What that means, though, is that when you put your pot of water on the stove to make pasta and you supply all that heat underneath it, it only will do this. It will only do this boiling thing when it gets to the right temperature. So when it gets to 99 degrees, it's still only evaporating at the surface. But when you get to 100 degrees, now all of a sudden there's enough energy inside the liquid throughout the entire beaker or throughout the entire pot that the molecules can separate from each other. They're overcoming their IMFs anywhere in the liquid, right? And so you get these bubbles that come, water gas basically is coming up through the water because those molecules have separated from each other. So here's a nice little chart that kind of describes the difference between evaporation and boiling point, or boiling. Evaporation, again, is only at the surface, and it can happen at any temperature, and it cools the liquid as well, like we saw that in the lab. Evaporation is a cooling process to the liquid. Boiling, however, can happen anywhere in the liquid, and it only happens at a certain temperature, and while you are supplying that heat underneath the pot, for example, you have to continually supply that heat in order to keep it boiling. If you turn off the heat, it will stop boiling immediately. And what's happening is the entire liquid is staying at 100 degrees Celsius that entire time. You're not really heating it up past 100 degrees Celsius. We'll get into that a little bit more in the next unit. But just remember that the boiling point is consistent. If your boiling point is 100 degrees, that means all the water stays at 100 degrees while it's boiling. Now, what causes boiling point, or what affects boiling point? Well, one that I've already mentioned is the IMFs, the intermolecular forces. If two molecules are hanging on to each other really, really well and really strongly, think like hydrogen bonds, they're going to separate from each other only after you get them really moving fast, right? They got to really be having a lot of energy before they'll separate anywhere in the liquid and boil. If they're holding on to each other loosely, then it won't take very much energy to separate them, right? And they will boil, they'll separate throughout the liquid at a lower temperature where you have less energy. Okay, it doesn't require as much energy to evaporate them. So the strength of the IMF has a big effect on the boiling point. The other thing that affects it is the atmospheric pressure, and we haven't really talked about gas pressure all that much yet, but we can just kind of visualize this with this simulation here, this little animation. We have gas molecules above the surface of any liquid. There's gas molecules flying around the room right now. If those gas molecules hit the surface of the liquid, they're going to prevent water molecules from evaporating, right? Whether that's just evaporation or boiling. And so the more pressure you have, the more collisions you have with those gas molecules on the surface, the harder it is for those water molecules to escape into the air. Okay, so the one thing you want to get in your notes is the more pressure you have, the higher the pressure, the higher the boiling point, because it takes more energy to get those water molecules to go up into the air, right? Because there's a force pushing back on them, basically. And those are really the two things that you need to know about boiling point, just that the stronger the IMFs, the higher the boiling point, and the higher the pressure, the higher the boiling point, okay? And remember, let's actually go back to this previous slide. The boiling point is confusing because it's just a number, it's a temperature, but it tells us how much energy, how hot do we have to get it before those molecules will completely separate. So if you look at this table here, I kind of forgot to mention this. These have different boiling points. So one is at 85, the next one is at 238. What that means is the chlorine doesn't separate, their molecules don't separate until they get to 238 degrees, which is relatively hot, right? This is actually in Kelvin, not Celsius, so that's a little bit different. But this boils at a much higher temperature than fluorine. Fluorine will separate at a relatively low temperature, meaning that they're not really holding on to each other as strongly. Okay, that's pretty much all you need to know about boiling point. Make sure you get all those notes down, and if there's questions, make sure you write those down as well. And this is Mr. Ugler signing off.